talk about gases specifically. So we've studied the states of matter, and this chapter is all about gases. Now this is a heavily mathematical chapter, so go ahead, you're going to need a calculator to work some of these problems. So we have three factors that are going to affect gas pressure. When you think of pressure, I want you to think about gas particles banging on the walls of a container. So we have things that will make that happen more or less. Temperature. As you increase temperature, the molecules are going to move faster, so they're going to hit the walls more often, so that will increase your gas pressure. Volume. And here we're talking about the volume of a container. The volume of a container is going to matter because if you have a sample of gas trapped in a certain volume and then you cut that volume in half, then those particles are going to be hitting the walls more often because it doesn't have as much room to move around. And the last factor is the amount of a gas. If you have more gas in there, you're going to have more gas pressure. Now today we're only going to talk about gas pressure, temperature, and the volume of the container. We'll pull in the amount of the gas a little later on. So we start our discussion about gas and those effects with our gas laws. And we'll start off with the combined gas law. Now the combined gas law is a combination of other gas laws. And we'll talk about those. There are three of them that make up the combined gas law. This one is all three, pressure, volume, and temperature, and how it affects gas pressure and their interrelationships. Anytime you're dealing with any gas law, temperature must be in Kelvin. Even if the temperature is given in Celsius and they want the temperature for the answer given in Celsius, these problems only work when the temperature is in Kelvin because we can't have negative numbers in there. The combined gas law looks like this. P1 V1 over T1 equals P2 V2 over T2. The P is obviously pressure, V is obviously volume, and T is obviously temperature. What the ones and twos mean is that they're describing two different situations. So what will happen is they'll say you have a gas at this pressure and this temperature and its volume is this. What is its new volume at this pressure and this temperature? So it's comparing the same gas just under two different conditions or situations. Here we can talk about initial pressure, volume, and temperature, and then the new pressure, volume, and temperature. And you have to read these very carefully so that you know from the word problem what's going on and keep those situations together. Now, a lot of times, and this is what the first day's homework is about, is if one condition is constant, it drops out of this combined gas law equation. So here we talk about the other gas laws. So if one condition is constant, it drops out of the equation. So if I have just Boyle's law, and this is just pressure and volume, we have Boyle's law, and here is a little explanation, kind of a simulation here of that. So I have some gas trapped in this container. I have said that my temperature is constant. So they're going to really try and keep this temperature constant. It takes a minute for it to stabilize. And I'm just going to mess with the volume. So I have my certain volume here, and we are at a pressure of 0.44, somewhere around there. If I take my volume and I make it much smaller, then those gas particles are hitting the walls of the container more, so that temperature restabilize. And under constant temperature, my pressure has gone way up. Now it's at 0.80, and I'm looking right here on that pressure gauge. All right, so that is Boyle's law. Now, all right, so Boyle's law. Since our volume went down and our pressure went up in that little simulation, we can say that that pressure and volume are inversely related. As one goes up, the other goes down. Our next law that we're going to talk about is Charles' law. Charles' law is where we have pressure constant. Now this is very, very realistic because we often in our everyday lives just experience temperature and maybe volume changes. But pressure is relatively constant. We don't go from pressurized room to pressurized room. So Charles' law is often there. Now, if we look at the simulation again, here, I'm going to say that we are going to have the pressure be constant. So we'll stick it at 0.8. And now it's just going to be volume and temperature. So I'm going to add some heat here and see what happens to my temperature. Our temperature should go up. And as my temperature goes up, you can see fire is being added. This volume is flexible. And so as my temperature goes up, my volume also goes up. So what we're going to see there is a direct relationship. Volume and temperature are directly related. So as temperature goes up, so does your volume. The last one is where we have pressure constant. This would be, volume constant. That would be like a rigid container, like a spray paint can. So that container is very rigid and cannot move. So that's Gay-Lussac's law. Yes, that is a pretty unfortunate name, but it is what it is. So let's have volume be constant. So we'll stick our volume there. And now we're just going to play with pressure and temperature. I'm going to remove some heat. So my temperature is going to go down, and we'll see what happens with the pressure, again, here on this pressure gauge. So if I remove some heat, some ice in there. My volume staying constant, and you can see as the temperature goes down, so does my pressure. So again, we have that direct relationship. All right, so Boyle's law, Charles' law, and Gay-Lussac's law all combine together to give us this combined gas law. Now, this gas law right here is given to you in the reference table. So all you have to do is be able to use it. So we're going to work some problems now on dealing with our combined gas law. So this is the first one here. And what I want you to do when working these problems is I want you to label your variables. It's very, very important that you do this. It keeps you getting the correct answer every single time. So gas occupying 75 milliliters. Milliliters is a measure of volume. Now that is the first volume I got to, so I'm going to call it volume 1. And then it says it is this volume at standard conditions. Luckily, from the last chapter, we know that standard conditions for a gas is 1 atmosphere of pressure and 0 degrees C, which is 273 Kelvin. That's when they say standard conditions, or STP, standard temperature and pressure, they mean pressure is 1 atmosphere and temperature is 273 Kelvin. And that's just something that you're going to have to know and be able to pick out. So that is one situation. It was this volume at this pressure and this temperature. Now we're going to mess with it. So we're into our second situation. It's heated to 17 degrees C. Well, that's a temperature. It has to be temperature 2. Our temperatures have to be in Kelvin. So that's going to be, I add 273 to it, so that's 290 Kelvin. While the pressure is reduced, so this is my second pressure. And what new volume is occupied by the gas? So V2 is what I'm looking for. That's half the battle right there, is identifying your variables. The other part that you really need to be successful at is rearranging your equation correctly. Now, some students will want to plug in the numbers to all of these variables first and then try and rearrange it. It actually is a whole lot easier if you just rearrange the formula first and then plug in your numbers. So that's what I'm going to do here, and I recommend that that's what you do as well. When you have the combined gas law, the easiest way to rearrange this equation is to cross multiply. You've done this in math class, and we're going to apply that math here. And I call it leveling the playing field. It's just going to make it a whole lot easier to rearrange. So it's going to be this times this. So P1, V1 times T2 equals this times this. P2, V2, T1. Now I have an equation, I have it partially rearranged. It's much easier to go the rest of the way. I'm looking for volume 2. So that's what I'm looking for. Now I need to get V2 by itself. So don't move V2, move everything else. So I need to divide both sides by P2 and T1. That way they cancel over here. And this becomes my equation. So V2 is going to be P1 V1 T2 over P2 T1. Now I'm just going to plug in all the numbers and check out the answer. So pressure 1 is 1 atmosphere. Volume 1, 75 milliliters. Temperature 2, and make sure you put the variables that you said need to go there. So temperature 2, not temperature 1, 290 Kelvin, over P2, which is going to be 0.97 atmospheres, times T1, which is 273 Kelvin. Put your units in there as well, because this allows us to figure out what the units are going to be at the end and check to make sure our units jive and cancel out. So atmospheres cancel, Kelvin cancels. All I'm left with are milliliters. So it's going to be multiply the top and then divide by everything on the bottom, multiply together. Remember that you are going to have to make sure that you plug it into your calculator, you put everything in one set of parentheses. But one set of parentheses. When you do this, you're going to look for sig figs. Your sig figs are going to be based off of your non-temperature numbers. And you want to look back at the problem to see the ones that are printed there. So in this problem, I have 2 sig figs, 2 sig figs. So my answer, I have to go with the one that's the least because we're multiplying and dividing. I need to have 2 sig figs in my answer. And so the answer to this one is 82 milliliters. All right. The next problem that we'll work with is a practice problem here, and we're going to be talking about its pressure and temperature. Now this one's a little tricky just because of the way it's worded. It says what pressure is required to reduce. All right, so they're talking about they want to find a pressure, but we're going to be reducing this 60 milliliters of a gas at standard conditions. That is a situation that has to stay together. So again, this is going to be V1, and standard conditions tell us that our pressure is 1 atmosphere and our temperature is 273 Kelvin. Then it says I'm going to reduce it to 10 milliliters, so this is V2, and this is T2 here with this temperature. Of course, it has to be in Kelvin, so that's 298 Kelvin. And we're looking for pressure, so P2 is what we're looking at. So you really have to read the context of the problem to get your situations together, and that is going to be very important for you to do. In this one, you should end up with 6.55 atmospheres. So work this problem out, make sure you can rearrange the problem correctly to solve for P2, and make sure you can get that 6.55